In this video, we're going to tackle the idea of related rates. All this really is, though, is applied implicit differentiation. We're going to be setting up some equations that define some physical context or situation. And then we'll use implicit differentiation to turn that equation defining a whole bunch of variables and how they relate to each other into an equation that relates the rates of change together. You can see why we're calling this related rates. All right, so let's just jump into it. The best way of doing it is to just do a couple of examples because we already have all the tools. This is just implicit differentiation. Here's our first context. We've got some water that's dripping onto a level wooden floor. The puddle is approximately circular. It's 6 inches wide currently, and it's growing in size. So here's our puddle. We've got this diameter all the way across, 6 inches diameter. We're adding drips to this puddle and increasing the area of the puddle at a rate of a half a square inch per second. Now, technically, we're not increasing the area. We're increasing the volume, right? This is a three-dimensional puddle. The puddle has a little bit of height off of the wooden floor, but we're going to just pretend that it doesn't for a couple of reasons. First, that height is going to be small and consistent all the way across, and so we kind of are adding an area if we look at it from a bird's eye view. Second, because reducing the number of dimensions makes this problem a little easier to tackle for us. So let's just deal with it this way. Our question is, how quickly is the edge of the puddle moving as it gets bigger? What I mean is, like, if our puddle gets a little bit bigger, our edge has now moved out to here. And then if it gets a little bit bigger, it's moved out to there. So we want to know what's the speed at which the water is traveling across the floor that we've got. What we're really asking, though, is not about the edge, and it's not about the diameter. It's about the radius. If our diameter is 6 inches, then our radius is 3 inches. And we're really asking, how quickly is the radius changing or increasing here? So this is a rate of change that we're asking about, and it's how fast is the radius changing with regard to time. That's what we care about. Then we have two other bits of information. 6 inches wide, a half a square inch a second. What are these things representing? Well, the 6 inches wide really is saying that our radius is currently 3 inches. And this half an inch squared per second, this is a rate of change of the area. So we'll call this dA over dt. So here's some information that we have. We have that dA over dt is equal to a half. We have that r is currently equal to 3, and we want to know what dr over dt is. We need to come up with some sort of an equation that links things together. Now, remember at the beginning, we're going to get those rates of change from using implicit differentiation. So we don't have to think so much about an equation linking the change in area to anything else. Let's just think about the two concepts that we have, radius and area. How do we link those things together? It should be pretty obvious. The most famous formula including pi, or involving pi here, is the area of a circle is pi r squared, right? What we're going to do is differentiate this with respect to time, with regard to t, time. We're going to assume that area and radius are both outputs for some input time, and we'll use implicit differentiation to differentiate this thing. Let's go ahead and do that. So if area is pi r squared, then that means the derivative with regard to time of area is the derivative with regard to time of pi r squared. This on the left is going to be just dA over dt. You could think about using the chain rule on this if you wanted. You could think this is really d over dA of a times dA over dt, right? 1 times the derivative of the area. Or you can say the area changes with regard to time by the derivative of the area with regard to time, right? Then we'll do the same kind of thing over here. We'll use the chain rule, and so we have 2 pi r, but then we need dr over dt as well. We're using the chain rule really on all of these pieces. Now, if you remember, we had some information. We had that dA over dt, that's an A, there we go, is a half, and we had that R is currently 3. So we can go ahead and just plug these pieces into place. And what we want to do now, let me get a green arrow here. Oh, that's gray. Here's green. Whew, fixed it. Now what we can do is say half equals 2 times pi times 3 times dr over dt. dr over dt is our only unknown thing. We can solve by dividing both sides by 6 pi, and we have 1 over 12 pi. The radius is changing at 1 over 12 pi inches per second. Cool. What does that really mean, though? Right? What are we actually saying here? What we're saying is that if we were to approximate this, grab a calculator, chuck in 1 over 12 pi, you're going to get like 0.0265 inches per second. What we're saying here is that we're really not increasing the size or the edge, I'll say, of our circle puddle that quickly. Our puddle is not marching along the floor that fast. It's a pretty slow change in radius. All right, here's another example. This is a classic related rates problem. A 16-foot ladder is leaning up against a wall, forming a 30-degree angle with the wall. The grips on the base of the ladder start slipping, causing the base of the ladder to slide away from the wall at a speed of a half foot per second. Oh no! At what speed is the top of the ladder sliding downwards? All right, so we have a pretty precarious situation here. Let's give a nice little sketch just so we can see what's going on here. Here's our ladder in blue. We've got a 30-degree angle up here. We have a 16-foot ladder here. And what we know is that our ladder is sliding away from the wall at a half foot per second. What you'll also notice is that means we're going to be sliding downwards at some unknown speed. If our ladder is a fixed length, right, and it slides away from the wall, it's also going to slide downwards. We might want to know some of these other side lengths for us, and luckily for us, we have an angle here. We know that 30 degrees is the angle on top, and as long as we know that, we are good to go. Because what we can do is say something like, well, sine of 30 degrees is going to be, maybe we'll call this A and this one B. So we'll say this is A over 16. So A is equal to sine 30 degrees times 16. Similarly, we could say cosine of 30 degrees is equal to B over 16. And that means that B is equal to 16 cosine 30 degrees. These are values that we can find pretty easily because we likely know what sine and cosine of 30 degrees are, right? That shouldn't be too big of a deal. We know that sine of 30 degrees is a half. So this is really 16 times a half, or 8. And we know that cosine of 30 degrees is root 3 over 2. So this is 16 times root 3 over 2. So we'll say this is 8 root 3. Those are kind of ugly values, but whatever. Well, one of them is. And that's fine. Now what we'd like to do, and maybe we'll call this side length C, just so we really can see what's going on. If we haven't clued in yet, let's toss a little right angle in here. And now we know what's happening, right? What formula are we going to use to connect rates of change of these side lengths and the side lengths themselves together? Well, we're probably going to use the Pythagorean theorem for a right-angled triangle with side lengths A and B and hypotenuse C. The lengths A squared and B squared add up to get C squared. Okay, so we're going to differentiate this with regard to time. We have a rate of change of A, right? dA over dt is half. And now we can go ahead and take these values And this rate of change, we've got this value here. We also have one other rate of change, but I'm going to keep that a secret for now. Let's go ahead and differentiate this thing. Okay, so we had a squared plus b squared equals c squared. Differentiate with regard to time. And all of these are going to go the exact same way because we're going to have chain rule showing up on each of these. So we have 2a dA over dt plus 2b dB over dt plus, equals, sorry, not plus, 2c dC over dt. We have a bunch of these values, right? We had that a was 8, b was 8 root 3, c was 16. So let's go ahead and write these in here. A was 8, b was 8 root 3, c was 16, and we had that dA over dt was a half. Perfect. This looks great. Notice we're missing two things now. dB over dt, that's the one we want to know, right? If b is this side length, we want to know what dB over dt is. That's really our question. But we're also missing dC over dt. What's that? Well, c was the length of our ladder. So the question is, how quickly is the length of our ladder changing? We have a fixed length ladder. It's not changing length at all, so we can say dC over dt is equal to 0. Great, no problem there. All right, now we can go ahead and input everything, and what do we have? We have 2 times 8 times half plus 2 times 8 root 3 times dB over dt equals 2 times 16 times 0. We don't have to worry about this. This is all going to go to 0. So we have 8 plus 16 root 3 dB over dt equals 0. And if we solve for dB over dt, we're going to get negative 1 over 2 root 3. Okay, so maybe we'll need a calculator to approximate what this is, just to do a sanity check on this, make sure it makes sense. If you do that, you're going to get like approximately negative 0.2887-ish. This is a rate of change in feet per second. The first question is, why is it negative? If we go back to our picture, it should make sense. As our ladder slides away from the wall, the height decreases. The height is shrinking. It's changing at a negative rate since we're falling downwards. Okay, so that's not too bad. And then we're falling downwards a little bit slower than we're sliding away from the wall. Interesting. So we're not falling downwards too quickly, but probably quick enough that we're not excited about the situation that we're in, right? Our ladder sliding away from the wall, falling down the wall. Hopefully we're not the one on top of the ladder. Okay, so that's how this goes. Last one. This one is probably our most involved example yet. It's a good one, though. Let's say that we've got some conical-shaped tank buried into the ground, storing some hazardous liquid. We are very concerned with the liquid in this tank. The tank is 10 feet tall with a maximum radius of 5 feet, meaning it looks like this. What I mean by maximum radius is the radius at the top. That radius is 5 feet, and then since it's a cone, it comes down to a point like this, and the height here is 10 feet. And so we've got some liquid stored in here. It was at 8 feet, but now it's dropped down to 7 feet. We can measure that by just like looking at the distance downwards from the top. Really, we're saying like, okay, it was 2 feet from the top, but now it's dropped another foot. So we're leaking here. That happens over the course of a day. What we can do is come up with a rate that that describes the change in height, right? dH over dt is negative 1 feet per day. Okay, so we're going to look at things in terms of feet per hour. So what is this? Well, it's negative 1 over 24 then, right? Over a 24-hour period, it dropped a foot. So we've got this negative rate of change that we have. And then we're going to say that while we're at 7 feet now, we want to know what rate the volume is decreasing. How fast is our tank leaking? So we're looking for some sort of a dV over dt. We have information about the height. we know that currently our height is 7 feet. And we also could find a radius here. We have some information about the radius, but notice it's not the information about the radius right now. This is the radius at the very top. Okay, so we need to come up with a formula that's going to link a bunch of this stuff together. We have volume equals 1/3 pi r squared h. This is the volume of a cone. Great, you can see what's going to happen, right? And hopefully we can see a problem. If you differentiate both sides, we have to know about a radius, and specifically we're going to get a rate of change of the radius in here. I don't know how fast the radius is changing. I don't even know what the radius is at 7 feet. Let's go ahead and draw another picture, and we'll give ourselves a bit of a head start on this. I'm going to graph just the cross view of our tank here. So this is what it looks like if we were to just stare at it from the side, right? Really, this is in 3 dimensions with a circle on top, but we're just going to pretend we're staring at it from the side. I know that this length here is 5. I know that this length here is 10. And what we want to notice is that here, this blue triangle with some unknown radius and maybe we'll say a height of 7, it's going to have the same ratio of side lengths because it's a similar triangle. Meaning, in general, if we had some radius and some height, we can say that r over h is always going to be 5/10. We're going to have this same ratio of side lengths because of the similarity in triangles. Meaning, let's just solve for r here. R is going to be a half of what h is. Let's take this, let's plug it in here, and never worry about the radius again. Here's a new formula for the volume of this specific cone with this ratio in side lengths. The volume is 1/3 pi times a half h squared times h, or 1/3 pi times a quarter times h cubed now. All right, finally, pi over 12. Let's get all the coefficient stuff right at the beginning, h cubed. This is the volume formula that we're going to go ahead and differentiate using implicit differentiation. Let's do it. All right, so V was, I already forgot it. It was a pi over 12, h cubed, right? There was an h squared from the radius, and now we've got an h cubed here. And let's go ahead and differentiate this with regard to time. This left side is just going to be dv over dt, which we want to know, right? That's the thing we're interested in. And now we've got pi over 12 times 3h squared times dh over dt. We're using some chain rule here, right? What we're really doing is saying this is pi over 12 times d over dh of h cubed times dh over dt. All right, so all this to say dv over dt is really equal to pi over 4 h squared dh over dt. And we have all of this information. We said our height was currently 7. dh over dt is negative 1/24, right? Let's go ahead and plug all this stuff in. We have pi over 4 times 49 times negative 1/24. All right, so let's go ahead and write this out. Negative 49 pi over 98. Is that right? 4 times 24. No, that's not right. 4 times 24 is 96. There we go. I can do arithmetic. Don't worry. That is our rate of change for the volume. Again, you can go ahead and approximate this with a calculator. And if you do that, you get like negative 1.6035. What are the units on here? Okay, we can follow this through. Height squared, so that's going to be feet squared, times feet per hour, so that's cubic feet per hour. All right, so this is bad news for us. We are losing a decent amount of this hazardous liquid out of the bottom of this tank. We better call somebody to fix this thing. All right, quick summary. What are we really doing here? First, hopefully you noticed, it is very helpful to sketch the situation, to get a picture. A lot of the formulas that we're going to be using are based on geometry stuff. And so most of the time, it's going to be easiest to identify that when we draw some pictures. On that note, when you draw your pictures, use smart labels and variable names. Connect them to things that they represent. Try and identify everything that you know. Specifically focus on what's changing. What are the rates of change and what are they changing with regard to? On these problems, you can notice that we have like feet per hour, right? That tells me I've got some sort of a length changing per time unit. So that's a derivative of something with regard to t. Think about what was actually changing and write it as the appropriate rate of change. Then what you want to do is find an equation. A lot of the time that's going to be based on some geometry stuff that you've sketched and whatever variables you've got. Sometimes, like in this last problem, we had to do a little bit of work to connect our equation to something that we had information about, right? Then we go ahead and differentiate that equation using implicit differentiation, and most of the time it's with respect to time. A lot of these related rate problems are things changing as time moves forward, which should make sense in application. Substitute all the things that you know and just solve for the thing that you don't. But really, this is just implicit differentiation with the normal math word problem strategies, right? Visualize your situation, label your variables carefully, identify what you know and what you don't. All that stuff is pretty standard problem-solving techniques in math classes. So the only thing that's new for us is implicit differentiation with respect to time. Use the chain rule. Make sure that you can see how that's going to work, and that should go pretty well for you. That's related rates. There's not much more to it than that.